4.031 Ga, onset of the Eoarchean and early proto-crust formation, marks the formal end of the Hadean Eon, following the cessation of major late heavy bombardment, meteorite impacts. Around 4.1 to 3.8 Ga Earth's surface cools sufficiently for widespread oceanic crust formation. In the Proto-Wyoming Craton region, present-day northern Rocky Mountains, initial mafic crust, basaltic, likely forms via mantle plumes or volcanic activity, similar to global patterns. No direct U.S. evidence, but detrital zircons suggest underlying Hadean Eoarchean substrates. Globally, this era sees the emergence of the first stable continental nuclei, but the U.S. area remains part of a dynamic, volcanic oceanic landscape. c. 4.0 billion years ago, Ga, the beginning of the Eoarchean event. The Earth's surface has just cooled enough to form a stable crust, though it is largely mafic and ultramafic, similar to oceanic crust today. The Hadean Eon, defined by a molten surface and heavy bombardment, is ending. 4.0 Ga, initial felsic crust formation and earliest zircon evidence. Detrital zircons in quartzites of the Hell-Roaring Plateau, eastern Beartooth Mountains, Montana, record the first felsic crustal events, indicating partial melting of hydrated mafic crust to produce tonalite trondhjemite granodiorite, TTG, precursors, key building blocks of early continents. These zircons imply a plume-influenced tectonic regime, where hot mantle upwellings melted the base of the crust, generating silica-rich magmas. This represents one of the earliest signs of continental growth in what is now the U.S., predating widespread plate tectonics, which may not have fully operated until 3.2 Ga. Implications: the presence of 4.0 Ga zircons suggests a pre-existing crustal seed in the Wyoming Craton, possibly recycled from Hadean materials. ND isotope model ages in the region exceed 4.0 Ga, supporting long-lived ancient crust. 4.0 to 3.9 billion years ago, end of the Hadean, start of the Archean Eon. The Earth's surface stabilized somewhat after heavy bombardment. Early continental nuclei, called cratons, began to form. In the southern Canadian Shield and northern U.S., Minnesota, Michigan, Wisconsin, some of the oldest rocks that underlie North America began crystallizing. The Wyoming Craton, beneath present-day Wyoming and parts of Montana and South Dakota, started to form. This craton would later become a major piece of the North American continent. Rocks from this time are rare, but zircon crystals up to 4.0 billion years old have been found in sediments, showing that crust was present. Throughout the Eoarchean, 4.0 to 3.6 Ga event, late heavy bombardment. Although theorized to have peaked in the late Hadean, significant asteroid and comet impacts likely continued into the early Eoarchean, delivering water and volatiles to the surface and causing local devastation. Event: possible emergence of life. The first biochemical life, likely prokaryotic archaea and bacteria, may have emerged around hydrothermal vents or in shallow seas during this era. Evidence in the U.S. There is no direct fossil evidence of life from Eoarchean rocks in the U.S. The oldest putative evidence of life on Earth comes from isotopically light graphite in 3.7 billion year old rocks in Greenland and microfossils in 3.5 billion year old rocks in Australia. 3.96 Ga, oldest confirmed zircons in U.S. territory. Discovery of detrital zircons dated to 3.96 Ga in Archean quartzites, metamorphosed sandstones, from the Hell-Roaring Plateau, Beartooth Mountains, Montana. These are the oldest dated minerals in the contiguous U.S., found in the Archean quartzite unit, deposited later, 3.5-3.3 Ga. The zircons are magmatic in origin, derived from eroded felsic volcanic or plutonic sources, indicating active arc-like or plume-related magmatism. Their morphology, e.g., oscillatory zoning, confirms igneous crystallization in a felsic environment, not metamorphic overgrowth. Geological context: The source rocks were likely TTG gneisses or dacitic volcanics in a shallow water or subaerial setting, eroded and transported into sedimentary basins. This event aligns with global Eoarchean zircon showers seen in places like Western Australia, Jack Hills, for 0.4 Ga zircons, but is the earliest U.S. record. Broader implications suggests the Wyoming craton had stabilized felsic domains by mid-Eoarchean, potentially hosting early hydrothermal systems or even prebiotic chemistry precursors. 3.9 to 3.8 billion years ago. The late heavy bombardment, if it occurred, was tapering off, with large asteroid impacts still reshaping Earth's crust. Protocontinental fragments began emerging across what is now Minnesota and Wisconsin, part of the Superior Craton. Conditions may have allowed the earliest microbial life to arise in shallow seas, though no direct U.S. evidence from this time exists. 3.8 Ga. Evidence of reworked ancient crust. Zircon grains and HF isotope signatures indicate reworking of 3.8 Ga felsic crust in the Beartooth Bighorn magmatic zone, Montana, Wyoming. These zircons, found in metasedimentary rocks, point to episodic melting and recycling of Eoarchean substrates during continental growth. Possible events include low-grade metamorphism or volcanic resurfacing, with evidence of subduction-like processes, e.g., ophiolite remnants in adjacent Canadian cratons, but inferred for Wyoming via isotopic correlations. In the broader North American context, this aligns with Eoarchean supercrustal sequences, e.g., sediments and basalts, in the nearby Slave Craton, Canada, suggesting a connected protocontinent. 3.8 to 3.7 billion years ago. The Isua supercrustal belt, in Greenland, near Laurentia, preserves evidence of life, and rocks of similar age existed in early North America as well. In the U.S. region, banded iron formations, BFs, began appearing in ancient seafloor sediments, marking early oxygen interactions with iron in the oceans. The greenstone granite belts that characterize early Archean crustal growth began to develop in the Superior and Wyoming cratons. c. 3.8 to 3.7 billion years ago. Event. The first stable continental nuclei, or cratons, begin to form through the process of accretion. Mantle plumes and intense volcanic activity create thick piles of magma that cool into primitive crust. These are the seeds of future continents. Evidence in the U.S. While no intact rock formations of this age exist in the U.S., the only direct evidence comes from ancient detrital zircon crystals. Key location: Jack Hills, Wyoming. Metamorphic provenance zircon crystals found in much younger metamorphic rocks in Wyoming have been dated to be as old as 3.8 billion years. These zircons did not form in place in Wyoming. They were eroded from ancient rocks that no longer exist and then redeposited as sediment. Their chemical composition, high silicon content, proves that continental-type rocks were already forming and being eroded in the region during the Eoarchean. 3.7 Ga. Peak crustal growth and magmatic pulses. Major pulse of TTG formation, as recorded by 3.7 Ga detrital zircons in Beartooth quartzites. These indicate widespread partial melting of basaltic crust, producing granitic melts that form the first substantial continental nuclei. Tectonic setting. Likely vertical tectonics, dome and keel architecture, rather than modern plate tectonics, with mantle plumes driving upwelling and delamination of dense lower crust. HF isotopes in these zircons show juvenile, mantle-derived, signatures with minor recycling of older crust. Environmental notes. Oceans were present, with possible anoxic conditions. Early life, e.g., microbial mats, may have existed globally, but no U.S. fossils from this era. Oldest U.S. stromatolites are 2.0 Ga. 3.7 to 3.6 billion years ago. Continental crust stabilization. The oldest surviving rocks in the U.S. date to this window. Examples: Minnesota River Valley gneiss, southwestern Minnesota 3.6 to 3.8 billion years old. Wyoming's Beartooth Mountains and Bighorn region, gneiss is up to 3.6 billion years old. These rocks represent some of the oldest continental crust in North America, the literal bedrock ancestors of the U.S. By the end of the Eoarchean, stable continental blocks existed in what is now Minnesota, Wisconsin, Michigan, and Wyoming, forming the core of the Laurentian continent. c. 3.65 billion years ago. Event. This is the age of the oldest identified crustal component that still exists as a recognizable geological unit within the United States. Key location, Beartooth Mountains, Montana/Wyoming. Evidence, the ancient gneiss complex. Within the Wyoming Craton, a part of the larger Laurentian Craton, geologists have identified gneissic basement rocks with protolith, original rock, ages dating to 3.65 billion years. These rocks have been metamorphosed multiple times, making their original nature difficult to decipher, but they represent the oldest known piece of the United States. They likely originated as volcanic rocks or tonalite trondhjemite granodiorite, TTG, suites, the building blocks of early continents. c. 3.6 billion years ago, the end of the Eoarchean. Event. The Eoarchean era transitions into the Paleoarchean era. By this time, the first durable continental cores are established. The geological record becomes slightly less cryptic, and more rock units from this later era are preserved. Legacy in the U.S. The 3.65 billion year old gneisses in the Beartooth Mountains and the evidence from the Jack Hills zircons prove that the region was one of the earliest places on Earth to develop stable, felsic continental crust. This ancient crust would act as a nucleus, attracting younger terrains through accretion over the next 3 billion years to eventually form the North American continent, and, much later, the United States. 3.6 Ga. Transition to Paleoarchean and sediment deposition. End of the Eoarchean. Continued but waning magmatic activity, with the last Archean zircons, 3.6 Ga, in Beartooth metasediments signaling stabilization of the Wyoming Craton's core. Proto-sedimentary basins begin forming, setting the stage for Paleoarchean quartzite deposition, 3.5 Ga, that entrains the older Eoarchean zircons. Early greenstone belts, mafic volcanics, may emerge, precursors to later supercrustal assemblages. Key implication: by 3.6 Ga, the region had a 400-million-year history of crustal evolution, making the Wyoming Craton one of North America's oldest stable blocks. Subsequent Neoarchean events, 2.7 Ga, would amalgamate it into the larger Laurentia supercontinent.